Good morning, ladies and gentlemen. My name is Mark Betcher, and on behalf of Nesma New South Wales, I'd like to welcome you and thank you for spending the morning with us for our morning at the test station. Hands up, who were here 5 years ago when we did it 5 years ago? Yep. 5 years ago. Yep. Who was here remembers the rain 5 years ago? So there was quite a few suggestions made yesterday that maybe we should be taking this on the road and going out to the farms and out west. We've got quite a bit to get through this morning, and we ask for your cooperation in making these processes flow as smoothly as possible. Just a few housekeeping notes before we commence. The ladies' toilets are located inside the building. The gents are just behind us, basically. You have to go in and around the corner. We request that all mobile phones be either turned off or put to silent, thanks. Any phones that are heard will be a subject of the next test. You'll have noticed, except for the sponsors, you'll all noticed a coloured dot or a gold star. Those with gold stars are lucky. On your name tag. They are the coloured groups. They're the groups that we're the viewing groups. So Max will be telling, or Martin will be telling. Martin will be mentioning about the colour groups. So each viewing group will have a different position around the test. We'll be conducting 4 tests, which will be followed by a walkthrough to witness the results. And then Max Carstead from Plus ES will give a brief talk on these results. The tests will also be streamed to the plasma screen in here. So if you haven't got a coloured, if you're not in a viewing group, I suggest you stay in the tent and watch it on the screen, and if you're short as well, stay in the tent and watch it on the screen, because you'll probably get a better view on the screen, to be honest. In between tests, we'll have presentations by Dane Horwood of Aaron Baker Switchboards, Martin Mulcahy of Plus ES, and Alan Mahoval of Eaton Electrical Industries. At the conclusion of each presentation, there'll be time allocated for questions, and we request that you please raise your hand and so we can find you and give you a microphone. In addition, there are glow wire tests being conducted in the area behind us, directly behind us, which you can hopefully view as well on the walkthrough. I think we've got a loop. The Plus ES guys have set up a camera loop, showing the results of previous tests, of glow wire tests. I'm not sure how much time I'm going to have at the end of the session, so I would like to thank the following people in advance: Martin Mulcahy, Max Carstead, and all the staff at Plus ES for providing the venue and for their expertise. Our platinum sponsor, Eaton Electrical Industries, and our gold sponsors, ABB Australia, APS Industrial, IPD Group, NHP Electrical Engineering Products, and Schneider Electric Australia, for partnering and sponsoring our event once again. My fellow NESMA members that contributed to the organisation of today's event, in particular Greg Redmond and Peter Silsby for putting together the board that we're about to destroy. Leanne Wilson and Kirsty Archer from Happenings Australia and her support staff in the coordination and organisation of today's event. So test 1 is going to be a bolted short circuit on main bus bars in the far right hand section of the switchboard. Note all other parts of the switchboards are isolated from this test. Bus bars are spaced at the correct centres. We've used bus bar supports which are commonly used in the industry. Supports at the top have a maximum spacing of 300mm, and the supports at the bottom have a maximum spacing of 500mm. A test current of 50 kA will be applied to the switchboard for 1 second. Objective under normal circumstances would be that the bus bars will withstand the test current. The switchboard will comply with the requirement of AS 61439. The bus bars shall not show any undue deformation. The supporting insulating parts shall not show any significant signs of deterioration, and it must be capable of withstanding a dielectric test after the short circuit. Our objective is to demonstrate what can happen when the bus bars are supported correctly and incorrectly. So we've put bus bars at 300 centres and bus bars at 500 centres. So hopefully Max assures me that one's completely going to be wrong, the other one we don't know yet. So. Max is a supervisor of Plus ES and the ASTA observer. He's going to give us a rundown on the test. We'll play it in real time, and we will play it in slow-mo as well. So for those that blinked when it happened, like me, hopefully we'll get to see it again. So, Max?
I'd just like to say that, just before we start anything, that even though Mark said Peter Silsby built the board, it was to Mark's design, so all the damage occurred was probably Mark's responsibility. Anyway, just looking at the test setup before we start the video, we can see that there are the red vertical buzz bar supports, as Mark indicated, at the very close spacing towards the top, and then at the bottom end we've got the wider spacing. Now, Mark was incorrect. I think he said it was a 1 second test, but that test was only 0.2 seconds. So what we were doing is on the, as you look at the screen, the far left-hand buzz bar was the phase that was had the asymmetrical peak put onto the buzz bar system, and the two adjacent phases, or the two middle bars, were in the return path. So it was a three-phase test. The current level was 50 Ka RMS, and the asymmetrical peak was 105 Ka peak. So what the damage that we saw, even though the test was 200 milliseconds long, would have been the same damage that occurs for a 20 millisecond test. The deformation of the bars was caused by the 105 Ka peak that was put onto the buzz bar system. So we'll just play the test through. So what you can see is the buzz bar on that far left-hand side was repelled from the other two, and what we've got is the current. You're seeing a bit of vibration in the bars, and that's as the phase rotation of current is occurring during the test. We do see, even though the vertical buzz bar system is supported at the very base by the bolted short circuit, it broke the bottom buzz bar support because there was so much deformation. And you may also pick up a little bit of slight arcing where that left-hand bar is hammering onto the side of the enclosure. Now, there isn't much arcing there because the voltage drop across the system, even though we're applying 400 volts onto the buzz bar system for the test, the voltage rise from the short circuit position to that 200 mils up the bar system is not great enough to create a lot of arcing. If it was open circuit, then we would have had the full voltage to earth in that area. The standard itself requires that the buzz bar system remain sort of intact. As you can see, the bars with the closer buzz bar support spacing have remained substantially intact, and so this sort of support system would be quite common for a motor control centre where you might have plug-in units, and one of the tests was to ensure that the plug-in unit could still be removed and inserted after the test. But of course that would not be the case in the lower half of the buzz bar system, and any plugs that might have been attached at that position would have been destroyed, and then more likely than not there would have been line side arcing and a reasonable sort of explosion. All right, I think that explains the test. Size of the bars, I think they're a 6.3 bar, probably by 50 mil, are they? I don't. Yes, so a 50 by 6.3. Now, what you will see in we have that little demonstration of the glow wire test. One of the other requirements in the 61439 is a whole lot of the 10.2, which is all about material science and the appropriate materials used in the construction of the assembly. And we have two versions that both look identical, both look like that red support. One support has passed the glow wire test and one has failed. So that's something to be very aware of if you are submitting a board for test, that the appropriate materials are used in your support to meet those material tests that are required.
How does the Permali class go in regards to global life?
Permali is an A-class material which that has a 70K temperaturised limit based on its paper-based material or an A-class material. And it is a laminated material, and Permali's always been, as long as it's used in the correct orientation, then it will be, it's always been very good up to the 50 Ka. What's happening now, of course, the extreme requirements that are put on assemblies when we're talking 80 Ka and 100 Ka ratings on assemblies, that's when Permali starts sort of struggling a little bit. Also, the fact that the temperatures that people are trying to run their equipment at these days, the Permali, with being an A-class, doesn't have a temperature rating that's up there against some of the moulded materials.
Thanks, Max. When we were designing, I didn't design this board, Peter. I did, Max. I had nothing to do with it. We talked about showing when we've done tests before over the years, and we've done a few tests here at the test station in conjunction with the guys here. We've always destroyed boards. We've always shown the worst case scenario. We thought it was important to show in that test especially that we do have successes and what happens in a success. So it's important to know that whilst we're showing you the worst case scenario, majority of testing that goes on here is actually being passed because it's being built correctly. So, thanks again, Max. Our first speaker today is Dane Horwood, who's going to give us an overview of Nesma. Dane is the owner and director of R.N. Baker Switchboards, which are located in Dubbo and Newcastle. Dane is a qualified electrician, has been in the industry for over 19 years, and also holds diplomas in business sales and business management. Dane has been an active member of Nesma for about 8 years now, and has just recently been elected as our honorary president of Nesma New South Wales. So welcome, Dane, to the stage.
Thanks, mate. Welcome, everybody. That watching that video then just reminds me of why I actually wanted to be an electrician to start with. When I was at school, I thought electricity was pretty cool because it seemed like magic to me. It's invisible, and you can see from that like how you don't see anything happen, but that's what the effect is. So I felt like I was a magician when I first started my apprenticeship. Although that's not a magic trick that you'd want to be seeing every day, would you? So welcome everyone. Thanks very much for taking time out of your busy schedules. We've all got things to do these days. Everyone wears being busy as a mark of pride and things like that, but to be able to take time out is really good for our association, and even more so I think good for you guys to see these types of things. So no, that's really good to see so many well-respected guests here too. Hopefully with Nesma's continued action and support, we can do more of these days, get you guys a little bit more closer to the actual dangers or protective dangers of what we see here today. So, and that's going to be my way. Okay, so I'm Dane Horwood, as Mark obviously mentioned. I am lucky enough to be the president at the moment of Nesma New South Wales. I feel very fortunate. For me, Nesma was something that I was a little bit nervous about being part of. And as far as thank yous go, a big thank you of mine actually goes to Mark himself, because when I had my first experience with Nesma, I was lucky enough to have bosses who encouraged me to go, and they said go and see Mark to start with. He made me feel very welcome. Here today is really me talking about my personal experience and why I wanted to get involved in Nesma. And I wanted to get involved in Nesma, looking back now, is because for me personally, it's really a terrible feeling not knowing what you're supposed to be doing, especially when that's your vocation. You're in front of your peers, you're challenged, you're questioned, you're supposed to have the right answers, and in often cases in the past I was left looking like a stunned mullet. So my boss is Bill Manusa. At the time, He's a very well respected member of the community, a switchboard fraternity, and he understood the value of Nesma and the potential gain it could be for myself and the company moving forward. Yes, so like I say, he encouraged me to go and speak to Mark, and Mark made me feel welcome. One of the biggest things for me is I was a little bit nervous, because when it comes to having to answer questions, technical questions on something that we haven't really been taught too well coming up, it was very confronting and exposing. And if I didn't have the confidence to speak to people that were willing to help me, like Mark and Peter and Scott are the people that helped me the most, I wouldn't have got any more learnings. TAFE doesn't teach it as well as it should, just because of the volume that is in the electrical industry. They're more focused on general practices and electrical principles, not specifically on switchboards. So how do we get the knowledge and skills required to be a confident switchboard builder? Well, we start with TAFE, and we have our employers, and there becomes a case where not all employers know exactly what they're doing either. And that's no fault of their own, it's just a lot to know. So I've turned to Nesma members and got that help and support that I've needed. They have been the source of my learning, and if they haven't been willing to help me and been there when I needed the help, I wouldn't have known where to turn to. I mean, they didn't always help me directly, but at least they told me where to go to. So again, that's another big thank you to the guys that I've mentioned before. But these guys are my competition, right? Well, why would they want to help me? The reasons that they would want to help me is because maybe once upon a time they felt like I did, and they didn't know where to get their answers from. They didn't know who to ask the questions to. Also too, maybe they wanted to create a level playing field for all the other builders in the industry to make it a little bit fairer, easier to do business, and maybe they just want the best for the industry, because after all, that is what Nesma is all about. It's for the advancement of the industry within Australia and the encouragement of manufacturing and members for appropriately designed quality switchboards for commercial industrial uses. And as far as I'm concerned, with my experience and the association with the members I have, that rings true. A little bit more stories of times where I was exposed and felt a little bit stupid. I had a little bit of knowledge at this point, but not enough. I can remember after working on a tender for several weeks and finally getting to the table where I got to speak to an end user about the client, he quizzed me on arc fault containment and special tests, and I just stood there looking like an absolute stunned mallet because I didn't know what to say. I pretty much walked away with my tail between my legs and didn't hear another thing about that job. Tender schedules, filling out areas of tender schedules I didn't even know what they were talking about. I had to call a Nesma member earlier on in the piece to ask them what temperature rise limitations were. And I didn't even know that what standard to use when I first started out. Again, they don't explicitly teach these types of things in TAFE. And when I first got my hand on 3439, I opened up the book, and it's not an instruction manual. It's a lot harder to read than that. Again, I had some Nesma members to help me through. I can remember I was challenged on how did I work out creepage and clearance distances, and I and ahed my way out of that one as well, so I felt pretty pathetic. Again, a Nesma member was there to help me answer those questions. Also too, it is a little bit hard to learn the exact right thing in this industry. There's a lot of conflicts between what a specifying engineer would want versus what the standards say. There's also a lot of dogma in the industry about what used to be, what works in the past, that should be okay, the thicker the metalwork the better, right? Or, that looks pretty good. That's really not the case. So, given the conflicts, there's always conflicts where someone says, yes, you need to build this switchboard and it needs to be compliant. However, we also want you to do these 5 or 6 other things which actually renders them non-compliant. So where do we stand? There's a lot of boards that get built wrong, installed, sent out there. Nothing ever happens to them. They still function. But that's only because there hasn't been an event, there hasn't been a fault. And the reason why they're getting installed wrong often is because of lack of knowledge. They're obviously getting built wrong, specified wrong, and we can't particularly blame the builders individually or specifically. We can't really blame the consulting engineers specifically because there is a lot of knowledge to take on board. And when we're in a commercial market, people are trying to get their product out there. People just want to win jobs. They want to do what they think they need to do to win the job. A lot of people don't like conflict. A lot of people don't want to go back to a consulting engineer. They don't want to be seen to throw up problems for their customer and their clients. But these are the things that we actually need to do, because how else do we learn? So if there's anyone out there thinking of specifying 4,000 amp stainless steel IP66 job and putting it outside, maybe just speak to a Nesma member first. Just saying. So that was my past experience with Nesma, and I got a lot of my learnings from Nesma members because I didn't know where else to turn. So thank you again to those guys. In the past, Nesma started in 1982 with a group of 5 switchboard manufacturers who got together to discuss industry issues. Those industry issues were based around issues with unions and suppliers. Thank Christ we work alongside suppliers these days, otherwise days like this wouldn't happen, rather than against them. So thank you very much to the sponsors and suppliers that are here today. The association continued to grow and gain support from consultants and supply authorities over the next 15 or so years. And then some interest was gained from Victorian members, where Victoria ended up branching out and starting their own division. Now we've gone full circle and we would like to try and look at making Nesma national again, but you'll hear more about that in the future. When it comes to the Victorian members, a shout out to a couple of people that aren't here who also helped me. Mina Shihada, David Webb, David Epps and Wayne Walker. Those guys were very helpful for me coming up. They were more than happy to offer their knowledge and even sometimes send me some documents that they probably shouldn't be sharing because they'd paid for them. But, you know, this is how the industry needs to work. It needs to be members helping members and members helping all you guys that are making the decisions and telling us what you would like to have happen. We need to have that. We need to have that rapport. We need to have that communication, and we need to be a lot more open to what other people are saying, because every time that we stop listening, we're missing an opportunity to learn something new. Let's just communicate a lot better. So that's the past of Nesma, and all throughout Nesma we've all been volunteers. No one's been paid for their work, apart from a couple of representatives who have to represent us internationally in travel. The president of Nesma, what we stand for I already mentioned, and again that rings very true to me, and I can see that based on the turnout here today that it is a lot of members helping members for the benefit of the industry. Nesma has given me personal access to things like days like today, so to Plus ES. I've been to test stations in Victoria through Nesma. I've also been to international seminars. I've engaged suppliers internationally just to get feedback and get a little bit closer to decision makers on IEC standards. We have representatives that work on the committees for AS3000, AS61439 and various others as well. We have representatives that assist us and giving us information with supply authorities, and we also work closely with the supplier authorities to help them out. Whenever there's a potential defect, we like to be able to get reports on those, do corrective actions, get that information out to the industry so that these things don't happen again, and the inspectors can use their time to more value. We, as a group, we talk a lot about supplier innovation. We get supplier interaction. We get some really good feedback on what's coming up in the industry. We get support and assistance like we are today. And without that communication internally and externally to our suppliers, we're obviously at a hiding to nothing. We also share our experience with OH&S issues, different insurances, human resources and business management. So it's a very good group to be a part of. The future of Nesma hopefully will be more of the same, but with better representation. There will be hopefully a lot more members working with members. Hopefully we'll be able to say that we have other states that are more involved. I'm getting more and more inquiry from Queensland, and speaking to Nesma members in Victoria, they are getting more inquiry from the likes of Tasmania, SA, WA, which we also do have some members as well. We get together every year as a national group and discuss national-wide issues, developments and changes within the industry so that we all can stay ahead. And in the future, we all hope that there is continued interaction between our suppliers, consulting engineers, and so on and so forth. And we hope to do that with better representation. So why is it important that we have groups like this, and why is it important to get things right? We live in a world of litigation. We live in a world of commercial constrictions, contractual obligations, all these different types of things. Insurance companies, they don't want to pay out for any reason that they could find. Me personally, I live on a fear response. I don't want to be personally liable for doing anything wrong, so I want to make sure I'm doing it right. And I believe that is also the modus operandi of all our other members. It's important to do it right because sometimes there is some murky waters between what the dogma is with the industry, what used to be accepted, what a supplier is saying versus what a switchboard builder has to achieve versus what a consultant desires and what an end user's expectations are. It's important to get things right so that we can encourage or continue to have greater consistency and transparency across the board. So with that, I hope my message is heard. I hope that we can encourage more members to not only be members of switchboard builders to be members of our community, but to be active members of our community. It generally seems to be a lot of the same people doing the same thing over and over. Again, big shout out to Peter, Mark, Scott, Sean, Bill, Greg, Norm. A lot of the guys that are here today, Jay, are really the ones that are taking a lot of time out of their busy schedules to do all this for free for the benefit of the industry and for the benefit of everyone else here. So a big shout out to Nesma and a big round of applause for the active members. Thank you.
Okay, second test is a bolted short circuit on the load side of a circuit breaker. I don't want to say anything wrong here, Max. Is the test one section been isolated? We doing that?
Possibly, yes.
Yes, possibly, yes. The setup is a circuit breaker mounted in its own compartment. There's no door on the front though. Circuit breaker is fed from the main bus bars. A bolted short circuit at the end of the short length of cable as required by the standard. And a test current of 50 kA for 0.2 of a second. The circuit breaker will withstand the test current and can be operated manually. We hope so. Our objective is that we'll show pressurisation of the functional unit and the output of a circuit breaker when performing a fault clearance within its capabilities.
All right, here we go, the next test. Just before I do that, just a flashback to, for want of a better word, to the first test. What was brought to my attention that I didn't mention or highlight perhaps was that the spacing of the buzz bar supports on that vertical bar system is really dependent on a combination of the physical size of the buzz bar and the strength of the buzz bar support. So what can happen is if you're going to a 10 mil bar that's hard drawn, high conductivity, has a lot more mechanical strength than a 6.3 bar. And so what you can do is start expanding that buzz bar spacing as long as you've got an appropriate support to handle it. So this test validated that for the 6.3 50mm bar that was installed, the spacing at the top side, the top end of the vertical bar system was adequate, and that the spacing, the larger spacing at the bottom of the vertical buzz bar run was not adequate. So they're the things to sort of also take away from that. So if you had a 10mm bar, highly likely we'd still get some distortion in the bar, but not as much. Okay, now to the test in the middle tier. What we have is a circuit breaker of unknown manufacturer origin. And what we have, even though I think someone might be claiming that it's their breaker now because it did do everything it was supposed to do. What we have is some cables going out on the load side terminals, and what we might do is just play through we've got a slow-mo of the test because there's a lot of arc product given out through the circuit breaker when it's operating. So this is the same fault level, the 50 kA fault level. We're just seeing the walls flash backwards and forwards. So that's all the stuff you missed because you blinked. Now what we're seeing is the circuit breaker detecting the fault. I haven't seen the oscillogram, but I would expect that the operate time of the circuit breaker was sub 10 milliseconds. So as the current came on, it has a high rate of rise in the current. The breaker detects that, and then it just turns the supply current off. We had the 50 kA line side test, conditional rating on the line side. And so the circuit breaker has operated. You've seen the toggle move to the trip position. You just see that bit of black insulation falling out now and bouncing on the trolley. That was one of the barriers or vents that's at the line side pole terminal. It just goes into the barrier that's on the top to stop inadvertent or contact with the terminals. So that operation, you've seen a little bit of afterburn because you've got lots of gases tumescing from the product that the circuit breaker is made from. What we are seeing is the circuit breaker operating successfully with that 50 kA fault level. So the amount of arc product and the pressurization that would occur should there have been a door on the front of that cubicle is typical and expected. So it's not like a small miniature breaker that's operating at a 3 kA fault level. You've got a serious fault level there, and when the contacts start lifting, because of the circuit breaker starting to operate, you are getting arcing at that main contact zone. The secret of the manufacturer to have a breaker that can handle the high fault levels is to ensure that that arcing gets away from the contact zone as fast as possible, and then it is put into the splitter plates and then expelled from the circuit breaker housing. If you kept that arcing and that pressurization inside the molded case breaker, it would just shatter and fracture the housing of the breaker. It wouldn't be able to withstand that fault level. So that's one of the unknowns for a lot of people that are just building their switchboards and come to the test station the first time, the amount of pressure that is generated inside a circuit breaker enclosure. What you've got to remember, the arcing at the contacts, you're superheating the air and then it's expanding at a great rate, so pressurising the whole enclosure. Now, of course, the smaller the enclosure you put the circuit breaker in, and without ventilation, of course, that pressure wave, due to the expanding air inside the chamber, is going to hit walls, sides, doors of the enclosure at the same ferocity, and that's where it starts putting a lot of pressure onto door hinges and door fastenings. And we'll see that with the next test anyway. One of the things to realise, because that breaker has tripped so quickly, the only support offered to those cables was a cable tie mid-span. What does happen if the circuit breakers are a larger let-through energy and you see more fault current in the load side tails, you can actually see them starting to whip around. Just as the buzz bars moved in that first test, the cables would behave exactly the same. And it's a matter of, if we were testing to 61439, that cable tie is deemed as primary current support. And so if we start blowing cable ties away, then that would be deemed a failure of support system. You are able to put boards together with some cables there, and if you can allow the cables to whip around a little bit, but if they do, they can't damage themselves or pull away out of their lugs or do damage to the circuit breaker. So it's better to have all that primary current carrying conductors supported in an appropriate manner so it doesn't cause damage to itself during a fault.
It was interesting because that was a pass. No, the last one, I mean. That was a pass test. That would have been considered a pass test. And you can see how much damage is done in a pass test. So just think about what damage can be done in a failure. So the importance, once again, of building correctly. Our next speaker is Martin Mulcahy, manager of Plus ES. Martin's going to give a presentation on AS 61439. Martin has a Bachelor of Engineering and over 30 years experience in the field of testing and measurement for the electrical power industry. He started at Sydney County Council testing laboratories as a trainee. He has had careers in instrument calibration, electricity metering, and now finds himself as the manager of Plus ES's internationally accredited Lane Cove testing station. So if we could welcome Martin to the stage, thank you.
Thanks a lot, Mark, for the introduction. So, hi again. We're talking about the, Max hates me calling it the new Australian standard because in actual fact, we've been testing to this 61439 standard since 2009, nearly 10 years. It's only recently, 2016, that Australia's adopted that standard to be Australia New Zealand standard. So we're already familiar with testing to it and the differences between, I guess, the old standard, AS 3439, which is actually still in effect. There's an overlap period that is in force at the moment for 5 years. So we have seen an increasing number of inquiries because that 5-year period is drawing to a close in 2021. So pretty much I'm going to talk about the changes that you would expect from the old standard and what's coming in with the new 61439. And we'll see how we go for time. I've only got 20 minutes, so I actually did a similar talk a couple of weeks ago at Engineers Australia. I had an hour and I ran out of time. So I've drastically wound back the slides. We'll see how we go. And we can talk a little bit about the documentation. Doesn't hurt to probably reflect on the kind of document that you get from running through a test program against these standards. So just quickly, Lane Cove Testing Station. We're Australia's only purpose-built high-power electrical testing facility. Our claim to fame is actually the high voltage test cell on the other side of the building, and we can draw 500 MVA fault levels. So that's 25 kA at 12 kV. It's enough to put a decent dip on Sydney's electricity grid, and we coordinate that with the control room. Because of that 500 MVA fault level, it allows us to be in the club known as STL. So STL is a short circuit test liaison, and it's all the overseas test labs as well. And they're like the Supreme Court or the High Court. So if we have a disagreement about an interpretation of a standard, we can refer our decisions to the STL. and they update these guides. So the tests that we perform here at Lane Cove are consistent with the tests that are performed all around the world. Been around for a while, so next year is going to be our 50th anniversary. We have to have another shindig like this. And you might know the brand names TCA. Ausgrid is the electricity network, and Ausgrid is the reason that we are here. However, recently, the last year or so, we've split from Ausgrid due to some federal legislation that required it. So because we're an external business, we provide public services. We need to be in a separate company called Plus ES. So that's why Plus ES. Yeah, and there's a picture of us in 1976. It's interesting. I like seeing the test station when it's all nice and shiny, new. But I also like looking in the background, seeing how Sydney used to look in 1976. That's North Ryde in the distance. Okay, so there is a new standard for Australian switchboards, the 61439 Part 1 and the Part 2. So there we go, SAI Global. You now have to buy 2 standards to learn how to build switchboard assemblies. The way it works is you have the Part 1 is a general part. It has all the general specifications, characteristics and verification tests that apply to low voltage assemblies. And then Part 2 is specific to the switchboards. And it supersedes 3439 Part 1. I should actually point out, the 2 white boxes are the titles on the standard, and I'll draw attention to the fact that it says IEC 61439 Part 1 or 2, and in brackets it's got mod. So Australia has introduced some variations to the IEC standard. So while I say it's the same, it is the same, but just with some Australian variations, and we can touch on those. So this table is pretty much it. Take a photo of that. That's pretty much the differences between the old and the new standards in summary. So there are some brand new tests that weren't in the old standard. That's the green section at the bottom. They're new design verifications based around the materials. So Max was talking about the glow wire test that affects the insulated supports. And it's in that green section at the bottom. But even though you would see similar tests in the old standard, some of those tests, such as temperaturised, dielectric, they're a little bit different. So we can talk about those tests as well. I'll just go through the new tests. I'll just go through the green section. So we've got corrosion testing, and it's simulated corrosion. So they're simulating, well, I don't know how long the period is that they're simulating, but effectively it's a combination of a damp, humid environment, and then they put it in a salt fog or a salt mist chamber, which accelerates the corrosion of ferrous metals. So there's 2 severities. You've got severity A and severity B. Severity A is for the indoor switchboards, but if you want to put one outdoor and have a corrosion verification, then you need severity B. As you can see, severity A is basically 8 days of testing in 2 chambers, and severity B is actually 24 days. It's amazing how much corrosion you can impart on some metal in 8 days. I've seen some corrosion samples come back, and you go, gee, I can't believe that happened so quickly. And I was talking to someone earlier, and these new tests, they actually introduce new conflicts. So I always find interesting, you have the IP of an enclosure, and then you have the temperature rise, and these 2 things, they fight each other. With these new tests, we now have new villains, or we have new conflicts, such as the corrosion test affects the ability to earth all your external components. So the old days of putting a star washer to cut through the paint cutting washer, well, now it's cutting through your paint protection, and it's exposing a weak point in your corrosion performance. So yeah, there's a new villain. Insulating materials, verification of those. It basically comes down to where you have insulating materials is a fancy word for plastic. So if you have a piece of plastic and it's forming part of your enclosure, you have to do a thermal stability test. If you have a piece of plastic and it's holding up a bus bar, or it's preventing you from touching a bus bar, then you need to do a glow wire test on that. So the glow wire test, there's 3 different levels, but the most common would be, I think you've all seen the demonstration. Hopefully, well, if you haven't, go have a look in. That's just in the room adjacent. You heat up a wire to a certain temperature, 650 degrees. If the plastic is just forming as part of the structure, and 960 if that piece of plastic is part of supporting a live part or a conductor. So 960 degrees. And pretty much you poke it into the plastic, hold it there for 30 seconds, pull it out, and then there's criteria around how long do things burn for, and if it drops molten flaming bits and sets tissue alight. It's these criteria. So it's interesting because, okay, Max explained, we discovered a support that was, a well-used product, and it failed the glow wire. Glow wire's not in AS3439. AS3439 has short circuit tests, and these supports were excellent. They passed the short circuit test, and now we're starting to test the new standard, and we know it doesn't meet the glow wire requirements. So how can we certify a product? How can we issue a certificate on a product where we know the supports, even though it might pass the short circuit test, how can we issue a certificate on that if we know it fails the glow wire? So yeah, it did bring up a sticky situation. Incidentally, in the end, we didn't end up issuing that certificate based on the glow wire knowledge. Thermal stability. This is a really strange test, but it's a verification test nonetheless. Put it in a heating cabinet, and you let that plastic soften or do whatever it wants to do, and you leave it outside for acclimatise for 4 days, and then you get a piece of cloth and you wrap this cloth around a probe. You put it on a balance so that the resistance that the sample offers you is now 5 grams or 5 newtons, and then you push the cloth into it, and then you pull it out, and then if there's any little bits of cloth stuck into the plastic, it's failed the test. So it's a strange one. Do you have to calibrate your cloth? I'm not sure. Anyway, we do our best. The lifting test. I think it's not a bad test, this one. I mean, I know switchboards are probably only lifted, twice, I suppose, in and then out. But nonetheless, you don't want the switchboard, with the eyelets poking through the top of the sheet metal to pull through. Probably not a bad idea to test it. So they've come up with this. We add some extra weights in there. We've got chunks of concrete and bits of metal chucked in a pile ready to weigh up switchboards. So it's 25% heavier, and then we swing it around on our crane, and you've got to sit it up there for half an hour, and then you've got to move it backwards and forwards at certain speeds. So yeah, it's a lifting test. So they're all the new tests. And I only mentioned, there's more there. I mean, there's UV resistance and there's impact and marking, but they're the tests of consequence, I suppose. The UV resistance, that's for plastic boards or boards made of insulating material that are outdoor and are affected by UV. Now, we don't really see, I can't remember the last inquiry that we had for a board like that, and and we haven't got capability to do UV resistance anyway. You've got to have all these UV sources, which we don't have. So, don't know much about that. The mechanical impact test. So, there's a mechanical impact scale similar to the IP scale. You know, it has a series of numbers, 1 to 10, and yeah, if you want to assign a mechanical impact rating to your switchboard, then you need to do this test. But you don't need a mechanical impact rating to be certified. So if you don't assign a rating, you don't do the test to get your certificate. So funny enough, we don't actually do that test very often either, even though we do have a range of hammers and devices to carry out those tests. And marking's one of those things. Again, most of the people, they engrave their labels, or they'll use some covering over the printing. And so this test is really only applicable if you just print straight onto a surface, and then we have to run around with alcohol or solvents to see if we can rub it off, type of thing. But most of the time, that's not applicable either. All right, so now we've got some same tests but different. So these tests are in 3439, but they're a little bit different. First off, if we talk about the temperature rise, there's a variation on the IEC with regards to the temperature rise table, a table of temperature rise limits, I should say. So you have this big table, and it has all the temperature rise values that different components are allowed to get to. So circuit breaker terminals, external covers, the operating handles. So all those things have a temperature rise limit. Now, Australia's added a couple of extra notes to the temperature rise table, which changes slightly the flavour of how you interpret those limits, and probably the most specifically, the one that we would think about most is the temperature rise limit on a circuit breaker terminal, especially where that terminal doesn't form the connections for the external conductors. So what a common scenario might be like a Form 4B board where you have some bus bar leaving the functional unit, the terminals. So you know that you're going to have a piece of copper bus bar connected to that outgoing unit. Because you know that you're going to have a piece of copper there, you don't have to worry about sticking to the 70k limit for external conductors. But now the question is, well, what is the limit that you put on those terminals? 3439, we used to stick with a 70k limit. IEC in overseas, not our doing, but the STL got to, well, not the STL, apologies. STL are actually a high voltage scope, but the interpretation in the overseas labs for a circuit breaker low side terminal with that bus bar was 80k, and not that we actually ever agreed with that, and we constantly lobbied the accreditation mobs, ASTA, KEMA, and point out the error in their logic with that limit. Nonetheless, horses bolted, that's what the limit is. Now, Australia has the opportunity to have an 80k limit on circuit breaker terminals when they have a piece of bus bar going to it, but we require a manufacturer to support that 80k limit. So the notes in the additional notes in the table, in our opinion, support that requirement, and so that's probably a fine difference, but nonetheless it is a difference. So if you want to put 80k on your outgoing circuit breaker terminals, we need a piece of paper to back up saying that that's okay. Diversity factor is different. This is a so AS3439, let's say we had an 800 amp outgoing circuit breaker functional unit. Now you could apply a 0.75 diversity factor to your outgoing units, and so what that means is you would have an 800 amp outgoing unit that you can only run 75% of 800 is going to be 600, oh my goodness, 600 amps. So Really, it's a 600 amp outgoing unit, but we're still going to call it an 800 amp outgoing unit with a diversity factor of 0.75. So on your certificate or your test report, it still says 800 amp outgoing unit, but it can only actually run 600 amps continuously. I'm talking, this isn't a temperaturised test. So, so there you go. It might not become obvious when you look at the certificate, 800 amp, and you see the diversity factor written below. So that circuit breaker never actually experiences 800 amps continuously, but it's still called an 800 amp unit. The new standard sort of takes care of that anomaly by requiring, if you assign a diversity factor to an outgoing unit, you now need to prove that the outgoing unit running on its own, because remember, diversity factor is for a group of outgoing units really. It's recognising that it's not realistic that that group is going to run every single unit 100% all the time. So this is the diversity factor. However, if you have an 800 amp unit running diversity factor 0.75, you still need to prove that that 800 amp unit on its own can run 800 amps. So it actually increases the testing quite a lot. Diversity factor is probably not as common a request as it used to be, because we would then have to go back and individually verify each outgoing unit can actually run at 100%. So that's a big change. Also, the test methods. So by far the most popular test method is, well, minimise the number of tests. So depending on how you arrange the incoming unit and the outgoing units, we can do a single test and verify the rating for the incomer and the outgoing functional units. However, there's also the opportunity to verify everything individually, so by components. That would be the second test method. And the third one takes it to the next level, another level. You've got by components, but also now you can rate bus bars. So you can rate a horizontal bus bar for a certain current rating, and vertical bars even if you wish. So yeah, they have added these extra ratings that you can now apply. Dielectric is pretty simple. It's it's not simple, but I mean, you apply a test value. You have a test voltage that you use to verify a certain UI or UIMP on the switchboard. So the values have changed. The 3439 is actually the values have reduced to come in alignment with the IEC. So I've tried to highlight in grey. I don't know how clearly you can see it there, but you can see we got values for, say, the high voltage power frequency withstand test, and they're dropping from a previous test voltage of 3500 volts down to 2200 volts. So it's significant, but the duration still, it's a 5-second duration. It's a pretty quick test. Frustratingly, the impulse test, I don't know if you see that at the bottom of that second table, the AS, new AS now requires 5 tests, and 3439 only required 3 tests. Now, you know, you get through 3 tests, you're probably going to get through 5 tests, but technically, we can't assign the rating based on those older tests. Mechanical operations. This is, I find this one, this is I shouldn't laugh at this, but AS3439 had 50 mechanical operations. Now we have to do 200. And when you're doing a double pole 6300 amp withdrawable unit, it's about that wide. 200 operations is, it's actually a lot of physical labour. What's even more interesting is that the circuit breaker standard, the 947 series, requires for a withdrawable breaker in its own cradle to do 100 operations. So there we go. You put it in an assembly, all of a sudden you have to double the number of operations. I haven't mentioned internal arc fault tests, so what we're actually going to see after my presentation is some arc fault testing, but it's not mentioned in that table that I presented, and the reason it's not is because still it's not a verification test. So you can get a fully verified switchboard assembly, and it won't have, or it doesn't need to have, arc fault testing in it. There are additional testing, it's in the appendix. The AS3439 had Annex ZD. This is probably a test that we're all familiar with. And that annex has been transported, just lifted up and dropped into the new standard. That would be another Australian variation to the overseas. That Annex ZT method, that procedure, is still in the Australian standard, which is good. However, the IEC made reference to the IEC method of doing arc fault testing, and so that is now available to the Australian standard. So there are effectively two methods now to validate arc fault performance, or internal arcing, not containment, but performance. Yeah. Oh, I don't know if you recall, if you went into the test cell, we had the white cloth hanging down on one side, and on the other side we had the checkerboard pattern of black indicators. So the checkerboard pattern is the indicator type for the IEC procedure, and the white cloth is the Australian indicator cloth. So basically we hand those cloths in front of the switchboards, and we do the arc fault, and one of the criteria, not all of it, but one of them is that the hot stuff doesn't get out and set that white sheet on fire. Yeah. And with the IEC, we've got the black indicators. Now they are positioned at the front of the board, but they're also on the sides and at the rear. So now we have a procedure for interrogating arc fault performance all around the switchgear. The AS, it was just positioned at the front. Okay, I've got just quickly on documentation. So certificates and test reports. Everyone knows the difference between a certificate and a test report. Both documents are going to have this information. So what did we test? Who made it? And who wanted it tested? Sometimes two different people. Could be, utility wants us to test a piece of equipment that they've installed. When we did those tests, and what tests did we do? What procedure did we follow? What the results were, and accompanying those results is we like to include lots of photographs to picture tells 1,000 words type of thing, and drawings are included to better identify the equipment that we tested. A certificate though, what is a certificate? A certificate is a test, or documents a test performed strictly in accordance with the standard and the procedure. If you get a certificate, you can be sure. Well, if you get a certificate from Plus ES, you can be assured that the tests are performed strictly in accordance with the procedures. That yellow document there, you can see that's an ASTA certificate. So we're accredited by ASTA in the UK, member of the STL, and so these documents are recognised all around the world. Plus ES also issue documents, but probably not as well recognised as ASTA. They document ratings, so certificates are able to list ratings that that equipment achieved. They are normally sealed documents for a bit of document security, and interestingly, certificates generally last for a while. Sometimes they outlast the company that commissioned them. And so you'll have new companies, new brands, and we're able to reissue certificates as vendor documents that for a new brand name, or still has to be made by the same entity, but they can trade as different companies. Test reports. Well, the test method may be from a standard, but it can also deviate from that standard. So a good example is maybe testing a portable earth or overhead line, and the standard says you've got to precondition it and you've got to age the fittings and all that kind of stuff. Well, that generally doesn't happen. The customer has a new design, it's come off factory line, and he wants to test it. So we'll notate that in the test conditions, and quite often we'll indicate on the front page why this is a test report and not a certificate, and highlight this is not a certificate because we didn't age the fittings, something like that. In actual fact, customers come to us with their own test methods. They might be doing an investigation or some R&D, so it's not unusual that they'll just have something totally made up and their own criteria, and so that we can issue a test report on that. But it is interesting to think that if someone gives you a test report for a piece of equipment, it doesn't necessarily mean that it meets a standard, or it could be just their own procedure that they've invented. For that reason, it doesn't assign ratings. So a test report is literally just documenting what we did, what the results were. And in actual fact, we can issue test reports for failed equipment. So we test something, it blows up spectacularly, and we issue them a test report saying it failed. So you've got to read those test reports and read the fine print and just make sure that the test report someone's handed you passes and doesn't fail. Anyway, that's it. Thanks very much for your time.
Test 3, which is a standard arcing test started on the load side of a circuit breaker. It will be performed with just a piece of 20 amp fuse wire on the load side of the breaker. Thanks, Max. And we'll show, our objective is to show pressurisation of a functional unit and the output of a circuit breaker in conjunction with arcing from a load side fault when performing a fault clearance within its capabilities. It's similar to test 2, except we've got a door on it this time, so let's see what happens.
This third test was a similar sort of circuit breaker, but this time enclosed in a compartment with a door on the front. The difference between this test and the previous test in the centre section was that the short was created by a bit of fuse wire, and the idea is the fuse wire, when it saw the fault current started deteriorated and started arcing between the load side terminals. The breaker saw the fault level, which was once again 50 kA RMS, and then the circuit breaker tripped. This time we didn't get to see as much of the arcing because, like we did in the centre section, and the reason was because the cover was in place. It's held on by 3 dome nuts on the right side and 2 pintle hinges on the left side. So effectively, the unit under test was pressurised by the arc products coming out of the circuit breaker, arc vents, and also a little bit of pressure that's formed by the fuse wire rupturing, and that's causing arcing on the load side terminals. What happens, of course, as soon as the arcing starts on the load side terminals, the circuit breaker is recognising the fault, operates, and then it turns the supply off to those load side terminals, and then everything being well and good, the equipment is just in a position with that final circuit disengaged. What we're going to see now is the next test will be changing that fuse wire short from the load side of the circuit breaker to the line side of the circuit breaker, which means that in this board arrangement there is no protective device between our test supply test supply position and the actual protective device that's in the unit. So the only thing that will be turning the current off is the test station circuit breaker. Probably I think the boys are intending to leave it arc the same duration, 200 milliseconds. So worst case scenario is that we'll have arcing on the line side terminals of that circuit breaker for 200 milliseconds. door could blow open, even though the fastenings look fairly reasonable. If it were a tongue arrangement for closing, I would think that there was a high possibility of the door flying open during the test. Once we're in a bolted arrangement, there's more likelihood of the bolts keeping the door closed. But what will happen is there's a lot more pressure on the hinge side, for example. It's just a pintle hinge, which we could see shearing of the pin on that side. But for all intents and purposes, the pressurisation of the unit between a standard arc fault test and a normal operation of the circuit breaker doesn't vary too much, and we get the same sort of reaction between. So we're just seeing the test run through there. You're seeing, because there's no real seal, the doors, if you want to call it, burping a little bit, and we're just seeing a little bit of bowing of the door, and we may just get a little bit of the gas release from around the top edge seals. There is also a small vent inside that compartment, and you can see at the very lower edge of the that unit under test, some arc products escaping from that functional unit just at the base of the unit.
So that was pretty boring, wasn't it? But switchboard manufacturers love boring. That's what we like to see. Our next speaker is Alan Mahoval of Eaton Electrical Industries. He'll give a presentation on arc fault quenching solutions. Alan is currently the technical specialist switchboard solutions and with Eaton Electrical Industries, and has held similar roles in the industry for over a decade. Welcome Alan to the stage, please.
Thanks, Mark. Thank you, Nesma, for giving us the time today. We were asked to do this. I wasn't sure what we were going to really present. We're not allowed to really make it product specific, but something that's, I suppose, topical to the industry. And in light of today, what we're doing, blowing up switchboards, and a lot of switchboard manufacturers would have in their specifications, would see a lot of arc fault requirements. I thought today, I mean, we all know about insulating bus bars, setting trip units on breakers, putting phase barriers, things we can do to mitigate arc flash. But one of the things that probably not as commonly known about is arc quenching systems. They're not very predominant, but certain manufacturers have them. We're fortunate enough to have one that Eaton has developed, and it's been around for quite a while now, so it's a mature product. So I wanted to give you an overview of that. Before I begin, I'm contractually obliged to talk about Eaton for a couple of minutes just to give a company overview. So I'll just go through a couple of slides quickly with you on that. As you see up on that screenshot there, there's a whole mishmash of companies. They're all companies that brands you might be familiar with in previous generations in their own right. They're now under the Eaton umbrella. So a few of those have made some real clever acquisitions. As a result of all those acquisitions, it's gone from a company that was very American-centric to a market now that's, or a global player now that's spread over many markets, over various markets across the world. Particular to the system that we promote here in LV, in our power distribution, is the biggest acquisition we had there was Moller. So anyone familiar with old Moller, going back in the time, that's pretty much where our products come from now. It's the next generation of that. Most suppliers like ourselves put up slides like this. There's not a solution or a market or a product which we don't have. So whether it's from your basic commercial right up to industrial, mining sectors, whatever else, there's a solution that can be found in all our product ranges. What people probably aren't aware of too, you'll see there's vehicles. Eaton does have a vehicle division, so it does all the transmissions and gearboxes for players like Kenworth and that, really highly regarded stuff. So those who are into their vehicle stuff would know that. The other thing a lot of people would know, there's a hydraulics division too, which is another highly regarded arm of the Eaton family. A lot of the hydraulics and a lot of the Boeing and Airbus planes that we fly around in, so they're quite predominant in that field as well. In our sector here, we're part of a region called APAC. It's our Asia Pacific region. There's 11,000 employees, 25 manufacturing plants. Worldwide, it's a $20 billion US dollar business with about 100,000 employees. So It is a major player in the market. And here in Australia, or Australia, New Zealand, we're a group of 250 employees. All right, without further ado, we're going to go on to our arc quenching system. System we got is a system called Archon. Obviously, safety is a major issue with switchboards. A lot of switchboard builders are required to have arc fault containment testing in whatever they build through various methods. And look, we'll just start with the definition of an arc fault. Obviously, it's a short circuit between active parts. It's the result of an arc flash is the serious part of this. An arc generally runs away from the incoming breaker, tries to connect all three phases. The major impact of all that, of course, is the extreme rise in temperature and pressure. There's statistics along the heat that it's many times like a multiple factor of the surface area of the sun. It's that severe. As we know, accidents do happen in our industry, so even those who've got the tightest of regulations on working on boards, whether they're live or dead, accidents do happen. There's a graph there. Disregarding where that graph came from, no matter what statistic you have a look on the internet, there's always an incident rate of accidents that happen in our industry. So in the green, or the taller bar there, is the number of reported accidents. In the orange, you have the ones that are due to arc flash incidences. This is taken out of a German data thing, but if you read statistics on the internet, in the US, there's 5 incidences a day. This is quite a prevalent thing. So with all best intentions on working on a board or the way the board has been built or having arc fault containment testing, it's all great and well, but as you see by that data there, the greater majority includes arc flash. A great majority of those people were done by skilled or qualified persons working on a switchboard. So in the arc quenching game, the approach is, like any approach when you're talking about arc fault protection, is time, is to kill the arc in the least or the quickest possible time. So the time that the arc is exposed is elevated exponentially by the time it takes to develop, is to the risk and the danger of the person. So the approach is to limit the arc time with something that evaluates the arc correctly and kills it in a real timely manner. So with the arc fault detection systems, they use two evaluating methods. One is light through fibre optics, and the other one is the rising current through CTs. So if only one triggers, it doesn't go off. You don't want accidental mishaps or triggers as well, so it needs both evaluations to occur for it to say, rightio, we're ready to shut this down. The architecture of the system, the pieces that fit into this puzzle, starts off with a master unit. That's the brains of the system. Not only is it the brains of the system, you'll see a whole lot of indicating lights in there. It's self-diagnostic, so every now and again it self-monitors. So you do have fault signals on the front there if an event were to occur. The slaves are part of the system as well, so they're spread around the board. The reason you have slaves, they only handle a certain amount of outputs per slave in terms of how many optic fibres you can take out of each slave. You can do it as a linear optic fibre, or you can do them as point sensors around the switchboard. And then you have the quenching device itself. So it's an encapsulated device. It's a one-blow device. The technology for actuating the bolt there that shorts out all the phases is the technology developed from what we use in our cars with our airbags. So you'll see there, the action or the quenching principle is before the trip, you've got a bolt which is placed in the guideway, all the phases insulated against each other. After the trip, after the actuation occurs, that bolt penetrates the insulation and a metallic short is realised. So here, we're going to talk about the function. In a normal operation situation, everything checks out fine. An occurrence occurs. Now, Both light and current sensors are both actuated. They both send a signal to the master trip unit or the master unit. This trips the quenching device. All of a sudden that bolt is actuated. The quenching device produces a short circuit. The short circuit is produced purely to take all the energy away from the arc. And that's what the quenching is there. That's how the arc is quenched. While that is going on, another signal is sent to the main breaker, and that trips out the shunt on the main breaker. So it disconnects power to the system. So the system's down, it's safe, everything's ready to go. To find out where the fault occurred, once that is eliminated, the board is still operable. When we talk about arc fault protection, yes, human life is the major principal factor in all this. The other part that people don't realise is that most boards that experience an arc fault are inoperable afterwards, so that's downtime. The replacement is lengthy. This one just needs a check, basically a visual check. Maybe if there's areas that need to be cleaned on the bus bar, the board's ready to go again. Here's some of the major statistics. So it's for switchgear assemblies up to 690 volt. The time there is the time that's the critical factor. It's under 2 milliseconds. There's nothing that's faster on this planet that will provide you this solution. The rated short circuit times, it goes from 65 up to 150 kA for all those ratings you see there. It's complete self-monitoring, as I stated before, and it's also EMC compatible. So part of the verification now is to have EMC compliant product within the switchboard, so it meets that compliance as well. So in the system itself, the quenching device you see is allocated in the space above the main incomer. You can put your slaves in various functional units around the board. From there you've got, like I said, your optic fibres out to cover all your main and distribution bars around the point, around the system. What's also a clever trick that you can do with this is you can have a spare lead connected to one of the slaves. So if someone's working on the board and the doors are open, you can pin the optic fibre to your shirt. You can go around the switchboard with the doors open, so should an arc occur inside the actual breaker unit and you're front facing it, the flash on your shirt will detect the arc flash and will quench the system. This has been declared you can work on an open switchboard with minimum PPE because of the under the 2 millisecond thing. Obviously we can talk about the effects of arc fault. You'll see it today. I don't know if you guys have experienced it in real life, but with the Archon, low risk of personal injury is the major factor in all of this. Like I said before, there's minor damage to the distribution system. It can operate after you've reset the switchboard. And the switchgear and control assembly can be restored after the fault has been eliminated. Without arc quenching system, the end of the bus bars, because the arc finds its way towards the end of the bus bars, it vaporizes, it burns holes through the side of the switchboard. The vaporized conductor material has coated the insulating clearances. All your internal segregations in that can be damaged as well. And then there's an exchange of the switchboard that needs to be necessarily facilitated. This system is certified, as you can see there, by an independent laboratory. Just speaking to the guys overseas at the factory, there never has been a common committee or a standard on this product because it's kind of never been done that way before, but they've come together. There is a standard now that will see these items perform to their own standard. So we're going to be one of the first manufacturers to go out and get that tested under that new alliance. So the first generation of Archon was back in '93, so it is a mature product with mature technology, proven. There's a big field of work out there of companies and these units being installed that have saved switchboards and lives. It can be used in other switchboard systems. It doesn't have to be within our own. I mean, it is a quenching device after all. And the important thing is it works whenever it should. So because of its self-diagnostics, it's always making sure that it's ready to act and there aren't any fault conditions within. some of the major companies that have adopted the arc quenching system, as you can see on that slide there. Now, in the current situation, to offer the same sort of, I suppose, personnel protection, you either have to use the moon suit you see there, or some use a remote racking system. Quite expensive options there. And again, here we're going to just show you a couple of little videos. You've seen a few videos today. This is our own videos of one where it's not protected and one where it is protected. Could I get you guys to play the one on the left, the not protected? All right, and we can go on the one on the right with the archive system. Okay, that concludes the presentation on this. If you need more information or you've got questions, I'm all happy with that. I'll be standing at the Eaton part. Like I said, the major advantages to this, like we spoke about before, most accidents occur when the switchboard is open with skilled personnel. Arc fault containment, therefore, is pretty much next to useless because the tests are done with the doors closed. You don't know how many times I get asked, oh, what happens if someone's got the doors open? All bets are off, you know, more or less. So think about when you're specifying this stuff. It's a nice to have arc fault containment in your specification. I'm not bagging it, but think about the practical real life situations. This system is not for everyone. Obviously, the application is obviously needs to fit the need. And if you're doing a lot of maintenance work, I see a lot of guys here in the fluoro guys here, probably industrially. This is very popular amongst oil and gas, mining, even critical power sectors. But you know, the prohibitive part about this is probably the cost. You know, you do pay for systems like this. But as you can see, what a world of difference it makes.
Thanks, Alan. It was very interesting. Okay, the grand finale. So the test number 4, Max mentioned as an unlimited arcing test, which will start on the line side of the breaker. Our objective is will show pressurisation of a functional unit with arcing from a line zone fault. The result will hopefully be more extreme, much more violent than tests 2 and 3. Thanks for that. Martin mentioned earlier that we've got a list of everybody's names here. Apparently the handle's missing from the breaker from that one, so before anybody goes today, we've got to check your bags, sorry. Max is just going to run through the final tests, and then that concludes our session today. I just want to take the time to thank everybody for attending today. I also like to thank Nesma New South Wales Committee for organising it. Plus ES again, and our sponsors for giving us our premises, and sponsors for partnering with us, and Leanne and her support staff from happening events for putting it on. We wouldn't be able to do this without somebody organising it all. So I'll leave you with Max, and I'll sign off now and say thanks and hope to see you again at the next seminar.
Okay, well, here we are again with the same scenario as the third test, but the variation is that we've put the fuse wire to start the fault onto the line side terminals of the circuit breaker. The previous test, we had it on the load side. We saw a few sparks coming out at the bottom of the unit under test, but the door remained closed and there was no real contamination of the external part of the assembly. And for all intents and purposes, the only thing we saw was the handle of the circuit breaker rotate when it went into the trip position. This next test is a completely different scenario. Bear in mind that the third test that I've just referred to was what we call in the Appendix ZD a standard test. So several manufacturers over the years have done these standard tests and then claim an arc fault rated performance for their assembly. One of the things that must also be remembered is that when you have arcing inside a small closed chamber, there's always the chance that that arcing can propagate to the line side terminals, or the component itself may have problems clearing and then destroy itself. This test would be called a special test under Appendix ZD, and if we run the film, we can... I say film because I'm old, you see. Anyway, so here we go. We've got a dramatic effect. The handle of the circuit breaker is blown clear of the door. One thing to remember is that to ensure that the fault stayed on the line side, in this particular example, the circuit breaker was left in the off position, so there was no engagement between the operating shaft and the handle. So that meant the only thing that was holding the handle on to the front cover or the door were the small securing screws, and you know they're only quite small. That said, a fault can, if the board were under some sort of repair, the circuit breaker was off and someone had left their screwdriver or had not terminated the circuit breaker correctly, or there was some contamination on the line side. I am led to believe that someone had problems with curry powder on the line terminals once. Is that correct, Mark? Anyway, that's what it is. Somewhere it might be a plant that's creating a dust that's conductive, and that also could lead to a line side propagation of a fault. Here is a perfect example where the assembly constructed met all the requirements for a standard test, but when we put the board to see how it would perform with component failure, then we had this quite drastic effect. As you note, because it was a bolted door arrangement, the bolts or the dome nuts have stayed in position. The pintle hinges, the top pintle hinge has distorted quite a lot, and that helped or aided in a bit of pressure relief. But both hinges have still remained reasonably intact. The assessment of the test, now normally if we're carrying out a test to Appendix ZD, there would be that indicator cloth, either the white if we're using the Australian ZD version, or the black squares, which is the IEC arrangement to 61641, would be spaced in front of the assembly. For the white cotton gauze, it would be 250 millimetres from the front of the assembly, and for the black IEC indicator cloth would be 300 millimetres from the front of the assembly. In a test with the indicators in position, we would expect that the hot gases and flame wouldn't ignite the indicator. We also look at whether the fastenings and fixings of the cover of the unit under test remained intact. By remaining intact means it doesn't have to be serviceable, but depending on what document you're validating your test to, the minimum requirement would be an IPX1 for 61641. But however, if you were going to consider that the board was still suitable for further energisation, so we're saying that the fault had occurred in that compartment, every other compartment hasn't seen any damage or arcing generated from that fault, so that unit can be isolated, and then the assembly passes a dielectric test and then can be deemed fit for emergency or further service until an appropriate remedial time can be scheduled to repair the assembly. And so in that instance, we're looking for an IP2X rating to that unit. The aim is that that's the minimum IPX requirement for an assembly that's in service. So if you're taking the board out and there's no requirement, then the board only needs to meet an IPX1, where 50mm hole is acceptable. And if you're taking it back into service, then the whole assembly must meet the IP 2X requirement. So I think it's fairly graphic. It was a white assembly, so next time you come here, the assembly will be painted black, and we'll be able to carry out the tests again. One of the other assessments is that parts are ejected from the enclosure as well. So if you look at the 1641, they do a measurement of mass, and so anything 60 grams or above, or that is projected towards the indicator or hits the indicator, is deemed to be a hazard to an operator as well. So it's not only the flame, it's parts that might be ejected from the assembly during that test.
That concludes our day today, and once again, thank you very much for turning up. I think it's been quite a successful day, and I think everybody would agree, and thanks again. Thank you.